So, ladies and gentlemen, dear audience, so I welcome you to the webinar Innovative Developments and Solution for Steel Lattice Towers. My name is Mike Tibolt, and I'm a research engineer working at ArcelorMittal Global R&D in Luxembourg since 5 years. So my research interests, among other topics, are the steel lattice towers made of hot-rolled angle profiles in high-strength steels. And today, together with my project partners from the project ANGELHY, we are happy to present you the recent developments in the field of steel lattice towers. Later on, we will have 2 additional presentations from Germany, from the University of Aachen, from Professor Kemper and Mr. Mirko Friehe, who will present us 2 very interesting presentations. One on wind loading on the steel lattice towers, and the other one is an automatic tool for an automatic optimization of steel lattice tower structures. So very interesting, and I'm really happy that they were volunteered to present it, and I am deeply grateful that they accepted our offer to present these 2 presentations from Foster projects. So before we start, I will give you some important information on the organization. So this webinar will be recorded, so there is a possibility, even if you cannot participate in live, to listen it later on. And also, if you have questions, there is a button Q&A in the Zoom where you can write your questions that we will be grateful to answer at the end of the webinar. So this is then during the discussion and closer topic at 12:30. So as you may know, the European network of transmission system operators in Europe accepts 80 kilometers of new transmission lines to be constructed in Europe until 2035 to cover the demand of renewable energies. Because now the renewable energies, they will be produced decentralized, and you need these new lines to transport the energy from the production location to the end users. And also the latest development in the telecommunication technologies, like for example, the G5 requires also the construction of new antennas. And so we need new telecommunication towers and or strengthening of the existing ones. And so in the future, new steel lattice towers need to be constructed for telecommunication, for energy transportation, and also existing structures need to be strengthened. And if you have now a look into the design of steel lattice towers, you became aware that all the designs of steel lattice towers, except especially for the steel transmission towers, they are based on knowledge coming from the 60s, 80s, so 40 years ago. And of course, in the Eurocodes, in the current codes, they are open questions that we have to answer to offer an optimized design of these structures. And that's why, together with the partners, we initiated this European funded research project, ANGELHY. So it is funded by the European Commission via the Research Fund of Coal and Steel, the RFCS. It started in 2017, will come to an end end of this year. And so we're going to present you the results that we obtained during this research that we carried out over the last 3 and 4 years. In addition, as I already said at the beginning, we have also research projects ongoing in Germany, which are funded by the German Research Association for Steel Application, which is better known under the name of FOSTA. And today we have 2 people from the University of Aachen, which will present also their topics. And this will be very interesting, and I'm really happy, and I thank so Professor Kemper and Mr. Mirko Friehe to be here. What I can say is, before we start, I would also like to thank the European Commission for the funding of the project ANGELHY, which is funded by the RFCS, as I already said. And now I would suggest that we start with the presentation, and I will now give, as it is stated in the program, the floor to Professor Yanis Vayas from the National Technical University of Athens, which will present you during the next 20 minutes the research project ANGELHY. Please enjoy.
Thank you very much, Mike. It's a privilege for me to welcome also in this event. Why towers and why angles? Isn't it an old stuff? But Mike made clear what we are facing in the future. That means a need of new towers for the transmission of electric energy through the renewable sources, and also 5G. So this is, and then also the towers, our towers in Europe get older, so we need also strengthening of them possibly instead of building new. So this is exactly the heart of our ANGELHY project, which I will very briefly present you here. So my presentation gives you only a navigation throughout this project. So I will not be going into detail. Details will be presented, and results of this will be presented by the next presenters. And you will see that a lot of people have worked besides those that present their work here, have participated in this project and have worked for its outcome. So the project was divided into 6 work packages, and I will go through, and each work package had also many tasks, so that I will navigate you through this and present you one slide for every work package and every task. So work package 1 is about market analysis, case studies, and code review. Work package 2 is steel and hybrid members. Here were the experimental and numerical activities for single angled members, and we speak always about equal angled members from steel or hybrid. Then work package 3 was on built-up members. Work package 4 was the validation and design guide, validation of the formulae and all the methods that were developed in work package 2 and 3. 4 was dissemination. Yes. The partners of the project were the National Technical University of Athens as coordinator, ArcelorMittal, who provided the specimens and participated in the market analysis, who did a lot for this project. Then University of Liège, this was the second academic partner of this project, with Professor Jaspa leading a large team, which did both experimental and extensive numerical research. Then Cosmote Κινητές Τηλεφωνίες, which was the telecommunication partner. This is the national telecommunication company in Greece, which is a subsidiary of German Telecom. Then it was the CTICM, which the French Steel Institute, Research Institute, which participated also very, very vividly in this project. And then Sika France, which was the partner which provided us with the material, the FRP material. So the project duration was 42 months, and you will see what we have been done during these 42 months. So the first work package was on market analysis, case studies, and code review. So it was divided into 3 tasks. In the task 1.1 was the market analysis on transmission towers, and all that has been said is the needs for installation of new lines, installation of new, for example, 380 kilowatt lines, or reinforcement of existing lines due to upgrading, combining direct current lines with alternative current, etc. This is a report. So I should say that each task was accompanied by a deliverable. So you can find, that's why I make a navigation about this project, because for each task you can find a relevant deliverable and published deliverable, and you can look at it and find it. Then we had case studies, which was both telecommunication and transmission towers, and 6 case studies, and comparison between the 2 codes that regulate the design of such tower. This is Eurocode 3. This is more for lattice towers, a general part, and EN 5341, which is the special European specification for transmission towers. Then we come at the work package 2, which is on which comprises the experimental and numerical research on of this project. So first was the task 2.1, was the test on hybrid on high strength steel columns. We had 2 large profiles. We had 2 profiles types, which was the equal angle 115 with 18 and 200 x 16. Well, material was S460, and you see various lengths, various eccentricities. And so we had not only for axial compression, but compression and bending. This was 12 tests made in University of Liège. And then we had, according to these tests, we developed rules which refer to classification, cross-section classification, cross-section design, member design, and the experimental validation. Then we move on to the tests on the hybrid members. You see what the hybrid members that were angled, which were strengthened by FRP plates, either externally to the legs or externally and internally to the legs. There have been 5 3-point bending tests, 8 in backlink tests. The cross-section here was smaller, was the angle 70 by 7. And these tests have been performed in the laboratory of the Institute of Steel Structures in Athens. Then, according to that, we have also developed design rules which deal with mechanical properties of the hybrid sections, safety factors, cross-section design, member design, and experimental validation. After that, it's a full-scale test. As you see, this was performed. We built 6 towers, complete towers, 7 meters high, and we test them with through pushover testing. That you see here that we had orthogonal loading, so it was they were pulled from at the top, and either orthogonal or diagonal loading. So we had several tests with failure of the legs or failure of the braces, which were both from steel or hybrid. So, and in order to detect the failure modes in the context of the complete structure. And then, according to based on that results, we made a guidance on analysis model for complete towers. And this is the contents of the relevant deliverable, which is introduction, code provisions, experimental validation, alternative analysis and design models, and proposed analysis. So we had proposed 4 possible levels of analysis and design models. Then we move on to work package 3. Work package 3 dealt with built-up members with 3 tasks, with 4 tasks. And you see what are the built-up members, the shapes of the built-up members, which were back-to-back angles, start button angles, and with equal angles, and start button angles, but with unequal profiles. So you see that there is a larger angle profile, a start button with a smaller one. That is for cases where you can strengthen conventionally a tower, a steel tower. So the task 3.1 was the test specifications, where the parameters of the test were determined. And you see that the member lengths range between 1.2 to 4 meters, and with different packing plates and different cross-section for the angles. Then the laboratory tests, they have been performed in the laboratory of the Institute of Steel Structures in the University of Liège, with very, very interesting results. Then parametric studies on these built-up members, and you see the parameters considered were the connection type, bolted, welded, the clearance, various clearances, 0.2, 0.5, 1 millimeter, the level of preloading, 0.2%, 0.6%, 60%, or full preloading, and the value of the friction coefficient. And then finally, in task 3.4 are the design rules. And you see here, for example, this is a table where you see the topic. Then in the second column, you see the existing rules and the specification, the existing rule according to Eurocode or according to the transmission tower codes, and then the new rules, the new proposals for code amendment. Then we are going to work package 4, where we have task 4 tasks. The task 4.1 is the probabilistic modeling of structure and loads. 4.2 is performance-based assessment. Then is verification and calibration rules and the design guide. So this is an important part of our project. So probabilistic modeling of structure and loads, as you know, the codes give prescribed value of loads, which is which refers to all type of loads, like wind loads, which is the main action straining the towers, or temperature or ice. But however, that you see that these loads are not have a probabilistic nature, and in this task, all the loads, like you see here, the distribution of the wind speed, or the air temperature, precipitation height, and those combined, those two, the air temperature and the precipitation, gave the probability of the ice thickness. So you see here how it was, the loads were probabilistic modeled. And then we come to task 4.2. This is performance-based assessment, where the codes you can design a few your tower as you wish, but then come the probabilistic people and the performance-based people, and they say, okay, let's see now, let's forget how you have designed your tower, but now I take the ready product and I check it how it is, and I assess it how it is behaving in a probabilistic, in a performance space. Does it fulfill the performance requirement or not? And this is exactly of the task of the work of task 4.2. So you will see very interesting results on the how transmission and telecommunication towers, ready design towers, how they behave under these probabilistic conditions. Then we have yes, okay. Verification, task 4.3 is the verification and calibration of rules. Various rules have been developed in task 2, in work package 2, concerning both mainly concerning the angle sections from steel sections, but now they were verified through a procedure and calibrated in order to develop the final proposals of our rules. And you see here one diagram, many of them were produced. Each point results to a numerical study. And so you see here, this is the comparison between numerical and analytical results for cross-section resistance through strong axis bending. A lot of them were produced, and you will see them in the relevant presentation. And then finally, the design guide. All these were introduced in a design guide. This is the contents of the design guide, where is the scope, notation, symbols, and abbreviations. Then we go to angle profiles, CFRP material, that means carbon FRP material, angles with CFRP strips, steel lattice towers, design rules for single angle members, for hybrid angle members, and for closely spaced built-up members. So here you see finally the naked rules, and for the justification, so in this deliverable are the rules, and if you wish to see the justification, it's in the deliverables of the other work packages. Now we come to task 5. Task 5 to work package 5, and this is here. Excuse me. So it has 3 tasks. Task 5.1 is the design recommendation for angles. And you see we have a table ready to send it to the European Commission for, so you see that Eurocode 3 now is in the period of public inquiry. So we have presented, we have prepared our contribution to that. Eurocode 3 does not provide specific rule for angles, but we are doing it. And so it's some of them exist for cross-section verification and cross-section design, but not for members design. So either we are giving, you see here in this column, we have our ANGELHY proposals, and for code amendments or extension of the code rules. Then is task 5.2 is construction recommendation for hybrid angles. So it's how to apply the FRP plates to the existing steel towers, and this is a guidance on the construction recommendations. Task 5.3 is finally the dissemination, and it is a part, this workshop is a part of this dissemination. We would like to share with the academic and the professional community and our students also, at least some of our students, the results of this project. And it's this workshop. We are not very fond that we are not in a room to share with you, to see you, and but we cannot change it. This has to be done through the web. So, and this ends my presentation. I thank you very much, and I give the word to Mike.
Yes, thank you very much, Ioannis. So this was an overview of the project content. And now, as it is also stated in the as we have it here on the agenda, it will be me who will now make a presentation on the case study design of a transmission tower. So I will start my presentation. And so what was the objective to make a case study design at the beginning of the project? First of all, we would like to identify typical typology of transmission towers in Europe. So what does a steel lattice towers for the energy transport looks like? Then we would also like to get familiar with the design of single towers. So as I said, single towers mainly means it was not the whole line that has been designed, but only the single tower, because the focus lies on the angle profiles and the structural behavior of the tower. The design, and this was a question that we had just a few minutes ago, the design has been carried out according to EN 50341 Part 1 2012, and in more detail you will see it was the German national annex, because we assumed the tower to be in a location in Germany. So this it would be Part 2.4. This design allows us a comparison to the rules that we had in Eurocode 311 and 3.1, and also nonlinear design methods that has been carried out at the University of Liège, to see what is the difference between these design codes. Because you can design the steel lattice towers for transmission lines completely according to EN 50241, but as you know, you also have rules for buckling and section verification in 1.1, and also for 3.1 for mast and towers. And we would like to highlight a little bit the differences. So, and this design case study was the basics for that. And of course, a case study also serves as the basis for further research within the project ANGELHY, as I said, comparison to other standards, and also to make this probabilistic approach. So what we did is, so we investigated a little bit the different tower typologies, and I present you here three main towers that we identified. This was the Danube tower, the barrel tower, and the single span tower. So if we start with the Danube tower, it has, as you can see, two cross arms, and each cross arms varies. So we have two circuits. One circuit per side, so one circuit has three faces that you can see on each side of the tower. You have a lower cross arm, which is longer than the upper cross arm, and the general height is between 30 and 50 millimeters on average, and the width, taking into account the largest cross arm, is about 30 meters. As we see, it is a very typical tower that we can find in Europe. For example, in Luxembourg, we mainly have this type of tower typology. They vary a line between 220 and 380 kilovolts. They are used in woods in urban areas. And in fact, they are, let's say, a compromise between the two other tower structures that you can see on the right, the barrel tower and the single span tower. Because the barrel tower, as you can see it already on the picture, is higher. It has 3 cross arms, also 2 circuits on each side, but as you can see there, each cross arms only varies 1 phase, and you have the middle cross arm, which is the largest, and here we can see the height is between 50 and 60 meters, so slightly higher than for the Danube tower, and the width is about 20 meters. Of course, if you can see, it is used in woods and also to cross rivers, and also for farms where you need a certain distance between the conductors and, for example, the cows and the animals in the field. So it's mainly used where you need a certain distance between the conductors and the soil. And this one is really a standard type in the UK. It's very common in the United Kingdom. Then we also have the single plan tower, as you can see on the very right side of the slide. It only has 1 cross arm. It has 2 circuits, and the cross arm, of course, it carries the 3 faces on each side of the tower. The height, it's smaller than the other two. It's between 30 and 40 meters, and the width is on average 40 meters. But of course, it has a big environmental intervention, as you can see it also on the picture. You need really a broad corridor on the left and on the right of the tower, because in addition to the length of the cross arm, you need also to respect some safety distance between the conductors and, of course, the next trees or for animals and urban areas. So it's a very width corridor that you require. It is mainly used in the area of airports because the height would, of course, be an issue for the planes. It has a large protection strip, as I already said. And in the former Eastern Germany Republic, it was really the standard type for the 110 kilovolt lines. And what we retained for our case study was then the Danube tower. This tower is called Danube tower because the first one has been built in the 1920s in Germany along in the Danube Valley along the river Danube. That's why the name came from. Of course, if you see the typology of the towers, you have 2 different types which were investigated in this project. You have the suspension tower. So this is what you can see here on the left, where you can see that you have hanging insulators. So meaning they just vary the weight of the conductors, the self-weight of the conductors, and also the ice loads on the conductors in winter conditions, as we had it, for example, today. The tower also carries, of course, its self-weight. And of course, you have the wind loads acting on the tower and also the transverse wind loads acting on the conductors. And in general, it has a lighter structure than the dead-end tower. The application of the suspension towers are, of course, a support of the conductors and to reduce, of course, the span of the line. So suspension tower, in fact, just carries the conductors. Then you have the dead-end tower, as you can see on the bottom left corner, the pictures. You can see that the insulators, yes, they are hanging. So they are not only bearing the self-weight and the ice on the conductors, but also the tension loads in the conductors coming from thermal extension, contraction, also coming from the sagging, and also the ice loads on the conductors and the wind loads. They will, of course, create a tension load in the conductors, and they are then transported to the dead-end tower, which transfers the forces down to the foundations. So the dead-end tower bears the tension loads, in fact, of the conductors, in addition, of course, to its own self-weight and the wind loads. And it is in general a heavier structure compared to a suspension tower. And the application is, of course, if you need a change of line, as you can see it on the bottom right corner, where the line changes its direction. End of lines, yes, but also where you have the transition phase between overhead lines going down to the soil to buried cables, as you can see it on the bottom left corner, where you would like to go down to the soil. You anchor the tension forces from the conductors to the tower, but also for straight lines, you use them, and you can see it when you're driving on the motorway, for example, that also dead-end towers are just used when the line doesn't change the direction, but this is due to have some redundancy in the system whenever a tower structure will fail, that there is, let's say, another tower that can bury the tension loads. For our case study, we located, and this is just an assumption, our tower in Saxony in the Erzgebirge in Germany, which according to the national annex of the Eurocode 1.3 for snow and 1.4 for wind loads, it is located in wind zone 2 and in ice zone 2, with a height below 750 meters. This assumption was taken to have also a certain wind and ice load on the conductors and also wind loads on the tower. For the case study, we, as I already said, we took into account two towers, types, the suspension tower and the dead-end tower. For the suspension tower, we say it is a straight line with some elevation differences to have a difference between the weight span and the wind span. And for the dead-end tower, as you can see on the picture here, for the cross arms and the conductors, we have an inclined line with a change in direction with an angle of 22.5% to the horizontal. So the angle between the conductors was 135 degrees, and also an elevation differences. The tower span that we took into account is an average value of 350 meters. The wind span is half on each side. So if we have a span on two sides of 350 millimeter that we just assumed, we also have a wind span of 350 meters. And the weight span that we take into account to calculate the self-weight of the conductors going to one tower, this is not from the middle of the line of the span to the other middle of the span, but the weight span is the distance between the lowest part of the conductor in one span to the lowest part of the conductor on the other hand, as it has been shown here in the picture. And so here the wind span was assumed with 525 meters. Some general information on the tower geometry. So we took a height of the tower of 50.2 meters for the suspension towers and the dead-end towers. The towers were assumed to carry two circuits of 308 kilovolt, and we have, of course, three phases on each side, as it is typical for these Danube towers. Here you can find, in fact, the small description of the conductors that we used. So we took 4 bundles, yes, and we have a steel core which is then embedded in an aluminium core. The steel core to stabilize the conductors, and the aluminium, of course, to have a certain conductivity of the lines. Then we have the earth wire. The earth wire is a cable that is really hanging on top of the towers, yes, really on the very top. It is used, for example, for lightning protection. We used 1 bundle of a conductor that you can see here. The numbers 94 and 15, these are the numbers of let's say fibers that you can see here on the picture. For the insulators, we took the quadricil insulator from the company Hubble with a length of 5 meters. Here you can see a little bit the pictures of the towers, the layout. So we have a height of 50.2 meters. The base has a distance of 6.84 meters, and the largest cross arms has a length of 31 meter. The lowest, the lower or the shorter cross arm has a length of 22 meters. This geometry was then implemented in the design software Tower in version 15 from the company Powerline System, which allows you to calculate the whole line or only the tower. And here we took only the tower. You could see here on the picture the implemented tower geometry in the software Tower. The loads and the design, as I already said at the beginning of the presentation, were taken according to the standard 50,341 part 2.4 2016, which is the German national annex of part 1. And we have 1 single tower design, so not the whole transmission line has been designed, and also the conductor design has not been done, but it was the loading from the conductors has been calculated as point loads and then applied to the insulators and the connection point from the insulators to the towers. It was a linear elastic design as it is prescribed in the standard, as it was more or less a pre-design to have a first overview on the main design formulas in the standard. We did not carry out the connection design or the foundation design. And we were based only on single angle members. So the design assumptions were, as I said, linear elastic design and first order theory as it is given in the main part of the standard. The lattice tower is considered as pin joint truss structures. In the numerical simulation, we use trusses and beam elements. Beam elements were required because we need to avoid planar joints. So planar joints are joints, numerical joints, which have no stiffness out of plane, and then you would have a kinematic structure. So to avoid it, we also choose beam elements to attribute stiffness out of plane to the nodes. The foundation were considered as pinned supports, and the eccentricities in the connection were taken into account via this non-dimensional slenderness lambda effective, according to Annex G of the 50,241 part 1. We only had axial tensile and compression forces acting in the truss element, so no moments. And the German national annex prescribes buckling curve C for the buckling resistance, so independently of the steel weight that you use, but I will come back to that a little bit later. Then to calculate the wind loads on the structures, we used method 1 of the main part of the code, which is a prescription given in the German national annex. Because we have two methods to calculate the wind loads on the towers. You have method 1, which means that you calculate the wind force per segment on the tower, and you calculate the resulting force acting in the center of gravity of the section. Or you have method 2, and method 2 means that you calculate really the wind loads on each members. But the German national annex prescribes to use method 1. Then also the wind and ice load on the insulators were taken into account in the software. But, and this is surprising, according to the German national annex, you do not need to consider ice loads on the tower structure itself. So meaning only ice loads on the conductors, but not on the tower structure itself. Which is quite amazing, because we can imagine that you have a big ice load, however, and ice accumulation on the tower, especially in this mountain area where we assume the tower structures. The ice loads on the conductors were determined by the German Meteorological Service and long-term experiences, so we were basing on ice load zones, in fact. For the dead end towers, the calculation of the tension forces coming from the temperatures, the segs and ice loads and wind loads acting on the conductors were calculated with an Excel sheet that I wrote based on the technical mechanical formulas for ropes, to calculate the conductors. Then we used steel grade S355G2 according to the product standard 10,025 part 2, so non-alloyed steel. What is important to note is that the 50,241 and even the German national annex only allow steel grades S235 and 355, G0 and G2 to be used. So no high strength steels like in S460 is strictly spoken allowed to be used. So in the numerical simulation, so we modeled all the primary and secondary bracing systems that you can see on the right-hand corner. So the orange one are the bracing systems, the green ones are the beams and beam elements, and the blue ones are the truss elements. So we did not model the connection, even if it would have been possible in the software, and also no modeling of the foundation, but they were just pin supports. Then the conductors have not been modeled, but point loads has been calculated apart and applied on the insulators. So the tower was divided into 7 sections and 2 cross arms, and we only used single angles. The self weight is automatically calculated by the tower, but of course, because we didn't model the gusset plates or the bolts. We estimate them by an adjustment factor of 1.2, so 20% has been added to the survey to consider the bolts and gusset plates for the connections between the angle profiles. The wind loads on the towers and on the insulators has been calculated automatically by tower according to the German national annex, because it allows to take into account different different national annexes of the standard, the software. And also the wind and ice load on the conductors has been calculated by hand. As I said, the conductors have not been modeled. The ice load on the insulators has also been calculated by hand according to the German national annex. The weight of linemans, because there are some load cases we have to consider that also mans are working on the line, so you have to take into account their weight, has been automatically determined by tower according to the calculation, according to the German national annex. The construction loads has been calculated by hand, meaning when you add the conductors, you have some cases where you have conductors only on one side and you have more torsional loading and so on. This has been also calculated by hand according to the prescription of the German national annex. And also the load combinations have been calculated according to the national annex. And here you can see the load cases that you have to consider according to the 50,331 part 2.4, so the national annex. You have 12 load cases, A to L, where you have the wind loads which are considered in load cases A to C, coming from different direction, X direction, Y direction, so in longitudinal directions. Then you have extreme and also the wind loads combined with extreme wind loads combined with ice loads. These are the load case D to F. Then you have construction and maintenance loads, which are grouped in a section in load case Y, and you have the exceptional loads like unbalanced ice loads, for example, only ice accumulation in one span and no in the other ones. These are considered into the load cases G to L. For the suspension towers, it is sufficient to consider A to G. For the dead-end tower, you have to consider all these load cases. Then for the weight of the linemans, they have been applied to members, so to angle members with an angle of less than 30 degrees to the horizontal. And the weight of the linesman were considered with one point load of 1 kilonewton in the center of the member. And then you can see the partial safety factors that you have to apply depending on the load cases. So the design checks which we carried out in this case study was only the verification in the ULS, so no fatigue, because in any case you do not need to carry out fatigue limit design, and also no SLS. What we did is we did the section verification, tension and compression according to Annex G3 and in combination with the German national annex, of course. The member verification like flexural and flexural torsional buckling also according to Annex G, chapter G4, and combination with the German national annex. Then we have the crossing diagonal checks for the bracing without secondary bracings, which has been carried out because it depends if you have tension in one, compression in the other one in the crossing diagonals, which could stabilize the other one. And here you have different prescription in the code, and this has been taken into account as given in 50,341 German national annex. Also the verification of the bracing inclination, meaning that the inclination to the horizontal of the diagonals should be less than 45 degrees to avoid to have too high forces in these bracings. Then we also have redundant member verification, where we applied in hypothetical transversal forces of 2% of the actual forces in the braced members to the members that has been braced. Then we have the verification for the linemans for members which were inclined with an angle of less than 30 degrees. And so finally, we did also an automatic optimization by the tower structure. So the software tower allows an automatic optimization by changing the angle size and angle type with the criteria to find the lightest structure with the highest utilization of degree. And you could see here the results for the suspension tower, and we came up for this kind of tower with a total weight of 17 tons. We did the same also for the dead-end tower, and you could see we end up with a little bit higher weights, of course, 66 tons. And what we tried is, even as I said, it was not allowed to use S460 steels, even thermomechanically rolled. It was an S460M that we used here in the tower, at least for the legs and for the main horizontal bracings, just to see and to get a feeling. Yes, it is not the correct number, it was just to have a feeling of what can happen. And we see that we can reduce, of course, the weight. But nevertheless, this is what we have to say, is that the code does not allow to use this high-strength steel S460 in combination with the formulas, because the formulas have been derived for lower steel grades, mild steels like S235 and 355. Nevertheless, we see that there is a need to extend these formulas, perhaps also to high-strength steels, and to capitalize, in fact, the advantages that high-strength steels can offer. So here I am at the end of my presentation. So now I will give back the floor to my colleagues, which will present you, in this case, the new rules for single and build-up angle members. So to Mr. Bezos and also to Mr. Beyer.
Thank you, Mike. So I will share my screen. Okay, this presentation is about the new rules for single and build-up members and will be presented by me and Mr. Andre Beyer. And it is split in two main sections for rules for single angle members and especially for equal leg angles, hot roll angles, and for build-up members, back-to-back connected or star button members. So the question is why to develop new rules for angles. There are so many documents. Someone can find rules in Eurocode part 311 or in 331 or in other documents as 5341. So why to do so? There is sometimes an inconsistencies between these two documents, or sometimes there are some missing rules. So there is a need for that. And in the most of the cases, in all these documents, the rules have been developed for double symmetric cross sections. So for I and H sections, and they said, okay, you can use these rules for angles. Have in mind for lateral torsional buckling that for I or H sections, we use curve A or B, but for angles, they say use curve D, Y. And additionally, through ANGELHY project, we have faced a new failure mode named segment instability that I will present you today, that requires also the development of a specific formula. So for all these reasons, there is really a need for a full constant set of formula to cover the design of angles. And as we speak about development of design rules, we have the design rules to develop design rules for classification and for resistance of the cross-section under different loadings, or design rules for the stability and resistance of members. How to do so? Through experimental tests. Professor Vayas speak about them. The 12 laboratory tests performed on large angle high strength steel columns in Liège with different lengths, different eccentricities. There is also a paper available online from thin wall structure in this topic. And then we perform some simulation to validate the finite element models through the tests, and then a large number of parametrical numerical studies and analytical developments to finalize the design rules. You can see here in the left figure, you can see some of the tests with different failure modes, a pure flexural one in the first picture, a flexural torsional in the middle, and a mixed mode from flexural and flexural torsional in the right one, or some figures from the design rules. Of course, it's not possible to go through all the design rules and all equation line by line or parameter by parameter today. So I will show you some important results, some highlights of them. And I will start with the classification system. There is, as you can see the table, there is a full program for the classification for angles, but you have to highlight here something, because in the most of the cases when we say class 3, we usually connect this with the instability of a torsional instability mode. This is not correct for angles, because when we have an angle, a pure torsional instability will never appear. Actually, it can appear when we load the angle in the shear center, but it is not the case for pylons. When we have a pylon, we usually load the angle in one of the legs. And a second important thing that we have realized here is that in all the cases, the limits of the classification are based on the slenderness of the compression leg. Here, I will show you an example, as I promised, about the inconsistency of the codes. In this case, you can see the C/T ratio versus the ultimate resistance obtained numerically. The plastic resistance is, as you know, calculated. And you can see the different results obtained if someone goes through the different norms. You can see if we use the Eurocode 3 part 1.1, there are some specific rules for angles that one can use. If we go to Eurocode 3.1.1 and we phase the angle as an outstant element, we can find another value. If we go through Eurocode 3 part 1.5 and we go through the leg slenderness, we will find another value. And if we go to Eurocode 3.3.1, which is dedicated for pylon and mass, we will find another value. And this is the value that fits much, much better with the numerical results. So you can see that there is a need to summarize everything and conclude in something. There are also design rules and formulas for the resistance of angle section subjected to compression or strong and weak axis bending that have been developed. And those rules have been based on the results from semicomp, which means that there is a linear transition between the plastic resistance and the elastic resistance. And you can see in the figure that indeed there is a linear transition between plastic resistance and the elastic resistance. And we can also highlight here the benefit of the results, because you can see with purple and red line the proposed results from ANGELHY, but you can see with the orange lines the results proposed by the current codes. You see the difference. Here we have a value of 10, while in reality it's close to 16. And also you can see the beneficial effects from the semicomp approach that we have adopted, because here we have the linear transition, while in the current Eurocode you move from the plastic resistance directly to the elastic one, which is not the case in reality. And I move to another interesting topic now, the members subjected in pure compression. There are also some rules developed, and this is very important because also, as Mike told you before, in the most of the cases in pylons, we have members subjected in compression. And the first good result that we have is indeed that in Eurocode 3.1, in the latest version, they propose to use curves A or B depending on the steel grade, which have been validated through tests and numerical simulation, and that's really nice. But the most important in this case is that we have observed a tendency of all the angles to buckle along weak axis, even if the instability mode is a flexural torsional one. I don't speak a pure torsional instability mode because, as explained, it's not possible to have it if we load an angle in the center of gravity. So this really simplifies a lot the calculation if we have to face an angle and design this resistance of an angle only in weak axis buckling. It is very important to have it in mind. I will show you also a slide later on through the numerical results, but it was also there are some evidence through the test. We have seen that even if there is a flexural torsional eigenmode, the angles have a torsion, have a twist in the beginning, but at the end buckles toward weak axis buckling. And what about a member subjected to a strong axis bending? In this case, we should have a lateral torsional buckling, and there are also some developments and some design rules. And here, the most important thing is that actually you should use a curve, a buckling curve, much higher than this one recommended in Eurocode, because in the existing code, one should use curve D, while, as you can see from the numerical simulations, we can directly move to curve A with a doubling plateau, which is very important. This is what I'm said, that sometimes in Eurocodes, they just extend the rules from the double symmetric sections to other, but angles, as we have realized, it's really a particular cross-section. Also, there have been developed some design rules for a member subjected to compression and biaxial bending. I will not go through the whole equations here, line by line. I will show you just the numerical validations, a lot of numerical validations. Here we have axial force and weak axis bending, axial force and strong axis bending, or axial force and biaxial bending. And we have also validated these rules through numerical tests. And as I promise you, here, in this case, when you have a member subjected to an axial force and a strong axis bending, someone really accepts to see a lateral torsional buckling. And indeed, in the beginning, the angle starts to move laterally, which is normal, but at the end, you will see close to the failure load, it starts going along weak axis. And again, we have a failure along weak axis. Also, the general method has been adapted to fit better for angles through numerical and experimental validations. There are some recommendations and deliverables that we have done, and also the numerical validation can be found. It's rather complex, so I will not go through this. Just have in mind that we should take into account only weak axis buckling and not lateral torsional buckling. And I will move to the last topic, which is the segment instability, as I said in the beginning. What is it? It's an instability that is associated to the buckling of more than one members forming a segment. And in this case, we have observed it for a transmission tower, and especially for the leg of the transmission tower. As you can see in this figure, we have the exterior member, or the main member, and we have the simultaneous buckling of the two diagonals that forming the segment. Of course, each one of these three elements can resist to the applied maximum forces. They have designed to do so, but the simultaneous buckling of the diagonals is something new and represents a new failure mode. You can see if we make a cut here, you can see that actually the diagonals move laterally about and bend about one of the geometrical axes. The main leg and the main length rotates along its longitudinal axis, while the other elements that closing the triangle and the pyramidal just translated. And there is a simplified model to cover this. As you see, the point is to evaluate the critical load. So there is a simple formula to do so. And with this first model, because there is a second one, it's very important because through a really simple formula, we can evaluate quite well the critical load. I will show you also numerical results. And the importance of this one is that it is independent of the number of the rigid triangles. So we could have more than 2, 3, 4, as much as we want. So we can use this simplified model for all the pyramidal configuration. But in this one, the rotation restraint of the main leg, as you can see here, is neglected. So there is a second model, a bit more complex, but again, through really simplified formulas that take into account this torsional rigidity of the main leg and all the equation based on the geometry and the cross-sectional material properties. So it's really easy for one to do so and to calculate that. Again, we aim to calculate the critical load, and we can go through the Mersenne-Rackin approach, and we can evaluate if we have the critical and the plastic ultimate load. We can calculate the ultimate load quite easily. So I will show you now an example, an application in practice. We had a full transmission tower model in a full nonlinear software. This is the configuration that we will have in the leg. And now you can see that we subjected this tower to different load combination, gravity loads with wind in one or the other direction on only gravity or only wind. And we obtain the loads in the two diagonals and also the critical load multiplier from the finite element software. You can see in 3 of the 5 cases, this eigen mode is the relevant one, which is rather important. And you can see here the prediction of the critical load multiplier based on the simplified formula, which is quite close. There is a ratio of 0.82, so it's really good approach, analytical approach. And if we do the calculation, we will see that the leg is rather slender. So from the Mersenne-Rackin approach, we can conclude that the ultimate resistance is based mostly in the critical resistance. So there is a need to evaluate better this value of the critical resistance. And this can be done with the second model, the final model, which taking into account the torsional rigidity of the member. And you can see in this case, everything is the same here, it's the same tower. So you can see in this case that the results are much, much better. Now we are close to 0.91. And we can say that, yes, with this simplified formula, we can predict rather well the instability, the segment instability critical load. And that's for me. I will give the word to Andres, so he continue with the built-up members.
Yes, hello. So I will continue now with the part on built-up members. Sorry, I will start the presentation. So as Zoe's for single-angle members, ANGELHY also studied the resistance of built-up members. As you might know, also in your code 3, part 1.1, built-up members connected back-to-back may be treated as an integral single member without considering any flexibility between the chords if the distance between the plates is less than 15 times the minimum radius of gyration. And there are other methods that exist for higher backing plate distances, but if we compare these methods, we will see that there's a high discrepancy between the obtained resistances. For example, here in this diagram, I've drawn some curves showing the resistance obtained for back-to-back connected angle sections. Using the overhead transmission line standard EN 50341, and on the other side, if it is compared to the use of Code 3 part 1.1, a method that is based on the principles given there. And we see that there's a really high discrepancy between these two design models. And therefore, we thought it's really important to have a clearer background on the design rules. So the objective of the study was already to study the resistance of back-to-back connected angle sections under compressions. So they are noted BBE in the following. For star-buttoned angle sections, here SBE or SBU, the study is a little bit wider and concerns also combined compression and bending. Okay, so in order to have and to develop a reliable design model, 16 laboratory tests have been performed in Liège, and CTICM performed an extensive numerical simulation campaign. So here you see the laboratory test matrix. We have performed 6 tests on BBE specimens under compression only, 6 tests on SBE specimens under compression only, so star-buttoned with equal angle sections, and 4 tests on star-buttoned angles with unequal angle sections, with one bigger angle section for one chord and a smaller one for the second chord. In this laboratory test campaign, we used a steel grade of S355. As Professor Vayas told already, we've varied the member length in order to vary the member slenderness. We have considered different number of backing plates, and finally, we have studied the influence of bolt preloading in the connections. So here you see one of the results for this SBU2 specimen, and clearly it's a buckling, flexural buckling that has characterized the failure load. So in order to go a little bit further on in our study, we also developed a numerical model. For example, the one given here for back-to-back connected angle sections. So in order to reproduce the behavior as precisely as possible, the members have been modeled with solid finite elements, the angle section themselves, as well as the bolts connecting the two chords and the packing plates also. So in the numerical model, we have considered all contact regions explicitly. To study the buckling behavior, we used an elastic, perfectly plastic material law. We introduced a geometric imperfection that is eigenmode affine with an amplitude of L over 1000 and residual stresses according to this residual stress model. So of course, for these complex problems, it was really necessary to validate the numerical model compared to the physical tests. And this has been done. And for example, here is the result we have obtained for this SPU1 specimen. So star-battened angle section member, build-up member with two different chords, a length of 2 meters and 20, and two intermediate packing plates, or two battened plates, two pairs of battened plates. And we can see that the numerical model fits rather well the laboratory tests. So laboratory tests with the straight line and the numerical model with the straight line with markers. So therefore, the numerical model appears to be further reliable, and additionally to the tests performed in Liège, we have also validated the numerical model compared to other tests that have been performed in the past. So here you see now the matrix of numerical simulation parameters. As for the laboratory test, we performed simulations on BBE specimens, back-to-back connected members, SPE specimens, and SPU specimens. We varied the distance between the packing plates, the member slenderness, and also the bolt pretension in order to study further on the influence. We studied fitted bolt connections, so then without any preloading, snug-tight bolts, also without any nominal preloading, and preloaded bolts, different steel gates, and different load combinations. So actual force for BBE specimens, and for SPE and SPU specimens, actual force and bending moments. So now we can go on to the results and the outcome of the numerical study. I will not be able to show everything, but here an example for BBE specimens with fitted bolts. In this diagram, you see the resistance characterized by the ratio between the ultimate resistance obtained in the numerical simulation divided by the plastic resistance, and depending on the member slenderness. Okay. The markers represent different packing plate distances A. So as you see here, the numerical results are nicely aligned with Eurocode-free buckling curve B. Okay, so in this presentation, the distance between the packing plates does not have any influence, because this influence is accounted for in the calculation of a relative slenderness. So here is the formula, and you can see that we've considered a critical actual force, including the influence of the shear stiffness, so noted as V. So here the formula for this effective critical actual force, accounting for a critical actual force of a member considered as integral, and the influence of a shear stiffness. And here the formulas, so nothing new for the critical actual force. For the shear stiffness, we could conclude that for connections with fitted bolts, the only influence that really should be accounted for is the flexibility of the cords themselves between the packing plates. But this equation, so for the shear stiffness, is specific to the connection type. And we have proposed other equations for other connection types. So for example, preloaded bolts. Okay, so for star-battened angle section members, subjected to flexural buckling and bending moments, we propose to use the similar interaction equations as for single angle members. So the format is the same, with some adaptations in order to account for the fact that it's a built-up member. So the interaction factors KUU, KVU, KVV, and KUV are calculated based on the critical axial force accounting for the shear stiffness. The exponent here is equal to 1.7 for the built-up members. The axial force resistance is based on buckling curve B and calculated with the critical axial force accounting for the shear stiffness. And there's a little reduction for the plastic bending moments, MURD for major axis bending and MVRD for minor axis bending, because of a bolt hole that is situated on the tension side. And finally, we have a lateral torsional buckling reduction factor that should be determined with curve A and a critical bending moment calculated based on the second order of area about the minor axis, accounting for the influence of shear stiffness. Okay, so if we apply these two interaction equations with these 5 specific adaptations for built-up members, we'll obtain the following results, again shown for one example of SPE specimens with fitted bolts. So you will see with markers the numerical results, and you can see here that all results, or most of the results, are safe-sided, so with values lower than 1 in this diagram. I've also shown the mean value and the mean value plus 1 time the standard deviation. That is already an indicator of reliability of a design model. And what we can see is that's still safe-sided. So the reliability, I cannot go on much more in the framework of this presentation, but we applied the Eurocode 0 approach in order to determine partial factors for our design models, and we can show that that we can use a partial factor of 1.0 for the design model for star-battened columns and also for back-to-back connected angle sections. Okay, so in this case, I already want to conclude this presentation with a summary of the design steps. So common for all types of built-up members, back-to-back connected and SPE and SPUs members, is the determination of the shear stiffness that depends on the type of connection. Okay, I've shown the example for fitted bolts. Then with this shear stiffness, we can determine an effective critical axial force and critic SV for the relevant buckling axis. Okay. With this critical axial force, we can determine the relative slenderness and reduction factor based on buckling curve B. And then after this step 3, we have specific steps for the BBE specimens. They are studied only under compression. Therefore, we can directly apply the buckling resistance. For SPE and SPU specimens, so there are several steps as the determination of a lateral torsional buckling resistance based on curve A, the determination of the interaction factors, KEG, with the critical axial force considering the shear stiffness, and finally then the application of the interaction equations. So with this slide, I have already finished, And I would like to thank you for your attention.
Okay, thank you very much. Yes, thank you very much, Marius and André, for your presentation. So the next presentation will then be from Sika, from Mr. Reygner, who will make a presentation on the hybrid angle members, on the CFRP materials, and also on the design rules that we can derive for strengthened angle members with this CFRP strips. So please, Sébastien, I will give you the floor.
Do you hear me?
Yes, Sebastian, we can hear you, but you should share your screen, please.
Do you hear me?
Yes, Sebastian, we can hear you, but you should share your screen, please.
Mike?
Yes, I can hear you.
Ah, okay. I can't share my screen.
You have to share screen. It shares screen.
It doesn't work. It was working. Okay, let me just try something.
Mike?
Oui.
Yes, I don't see Sebastian.
Okay.
Yeah, he's back.
I'm back. I'm back. Sorry for that.
So you should be able to share your screen using the button.
Yes, it works.
Okay. Okay, we see now. Okay, perfect. Thank you.
Thank you. Sorry for this little delay. Let's talk about hybrid angle members. Now the combination of steel and FRP materials. In the first part, I will present you an overview of FRP materials, and I will go further in detail with the use of these materials for the ANGELHY project. And then Konstantinos will explain you the results and the design rules regarding experimentation tests we made. So as you probably know, FRP materials or composites are widely used in the industry like aerospace, maritime, transport, or sports, but also in construction. For your information, the use of composite materials in construction began in the late 80s. And now it's widely used also in the construction field, especially for concrete strengthenings to strengthen structural elements in buildings, for example, like slabs, beams, or columns, or if you need to create openings and strengthen them, openings in slabs or beams also. It is the same idea in bridges when you have to strengthen slabs, beams, or piles, but also in any other civil engineering concrete structures like tanks, wastewater tanks, silos, or chimney or refrigerant. But first of all, what are composites? Composite, by definition, is a mixture of hardened matrix and a reinforcement. So in construction, the well-known composite material is the reinforced concrete. You mix the concrete and reinforcing bars. In a fiber reinforced polymer, FRP, the composite is a mix of polymer resin, which is the matrix, and the fibers, which are the reinforcement. But which fibers do I have to choose for my application? Because we have various fibers on the market. For instance, glass, aramid, or carbon. These three fibers type have advantages and disadvantages. It depends on the target you want to reach for your application. For example, for the ANGELHY project, the goal is to do a structural strengthening application. So if we look at glass fiber, we see that it has a really low stiffness, low strength, so it's not very useful for a structural application. Aramid is very good in impact situation because it can absorb energy, but it's really sensitive to humidity. So it's not very useful for structural application as well. However, carbon fibers have high stiffness, high tensile strength, and high durability. So it's the perfect match for a structural application in construction. Even if it is the most brittle fiber, the tensile strength is so high that you never reach the ultimate tensile strength in the construction application. Moreover, the literature highlights that carbon fibers are the best solution for structural steel strengthening as it is for concrete structures because of the following points. After that, you have to combine these fibers with an appropriate matrix, a polymer resin, and the most performant resin on the market to be combined with the carbon fiber is the epoxy resin. So finally, the best combination for a structural application is a CFRP, carbon fibers reinforced polymer. And for the ANGELHY project, we have provided FRP materials and adhesives. Sika carbodure laminates had been chosen to strengthen steel members. These laminates have to be bound on the prepared steel members by using an epoxy adhesive, which is called Sika 30. Regarding the Sika carbodure laminates, we only have one thickness of 1.2 millimeters. Several widths are available from 5 to 15 centimeters in width, but due to the steel angle dimensions, 70 by 70 by 7, we had no choice but to use the Sika carbodure S512, which provide a cross-section of 60 square millimeters for the ANGELHY project. This Sika carbodure laminates has very high tensile strength, as I previously said. As you can see on the table, it is about 3,000 megapascal in tension. And you have to note that all these Sika carbodure plates have a unidirectional fibers orientation. All the tests are made in one direction, and that's why you have to choose in which direction you want to strengthen your structure. Then, as I previously said, we have to bond these laminates on the structure thanks to the Sika 30, which is an epoxy adhesive, ready to use thanks to the two components. You just have to mix them together and get a pasty and thixotropic resin, which enables the laminates to stay in place without any additional support. Please note that the Sika carbodure laminate is very light too. That's a big advantage for the construction field. Finally, the Sika 30 has a CE marking according to the European standard 1504 part 4 concerning the product for rigid and structural application. I will not going to describe in detail the application, but just keep in mind that you are working with epoxy products, so it's really important to work with safety tools and safety equipment. And all these recommendations about storage of the product and how to note the traceability of each product you use on your construction site. All these recommendations are explained in the work package in the ANGELHY project about the recommendation for construction. The main point is the steel substrate preparation before applying the laminates. Note that Sika Dur 30 can bond to degrees galvanized substrate, but it depends on the target bond level that you want to reach. And the literature said that the best solution is to prepare the steel substrate by sandblasting with a grade of 2.5. As you can see on this picture, that's the preparation you have to reach for a steel substrate. The important sentence is the following: any remaining traces of contamination shall show only as slight stains in the form of spots of strips. If angles are painting, the sandblasting preparation will remove paint and galvanization. So it's really important to proceed to the application of the laminates just after the substrate preparation, or to protect the substrate after preparation for the future work in order to avoid any start of corrosion. At the University of Athens, we prepare some samples for tests. The university has defined the length of the CFRP application needed for experimental tests. That's the reason why we only prepare one part of the angle members. After that, you have to mix the Sika Dur 30 at least 3 minutes by mixing component A and B together. The important point is to avoid any inclusion, air inclusion while mixing. And after that, another important point is the double bonding. You have to apply a layer of Sika Dur 30 on the Carbodur plate, but also on the prepared substrate. And after that, you use the application roller to ensure a good contact between the substrate, the resin, and the plate, and to be sure to not have any air enclosed in your hybrid member. Now I hand over the presentation to Konstantinos. We will present you the test results.
Good morning to everyone. Okay. I continue to talking about design rules and experimental tests in hybrid members. I will start with a test on hybrid members that were performed at the National Technical University of Athens the previous year. Hybrid members consist of an angled steel section and an FFP plate placed externally or both externally and internally to angled section. The set of tests included 5 bedding tests and 16 compression tests. In the bedding test, 3 of them were about bending about minor axis, and 2 of them were bending about geometrical axis. Regarding compression tests, in 2 of them the load was applied centrically and without any eccentricity, and the rest of them various eccentricities were implemented that corresponded to combined compression and bending condition. strong axis bending or weak axis bending. In bending tests, different types of failure occurred, depending on whether the FRP plate was under tension or compression. In the first case, we had the gradual fracture of the fibers. In the other case, we had either a sudden break in the FRP plate or a detachment of the CFRP plate when also shear strain existed simultaneously. In all compression tests, global backing of the hybrid member occurred without any debonding of the FRP plate or any local backing of the member of the steel section or the FRP plate. After that, after the experimental test, we have prepared some design rules for hybrid members. First of all, cross-section properties are calculated for the new hybrid section. Centroid, equivalent area of the section, second moments of area of the section, etc., are calculated for the hybrid section. For the calculation of the section resistance, a component that corresponds to the FRP contribution to the total strength is added to each formula as is indicated with the red line in this slide. As you can see, for each material, a separate material factor is used. In addition, for the CFRP plate, for FRP material, a conversion factor is used. In the case of pure compression, only in the case of pure compression, a reduction factor equal to 0.5 is used to reduce the ultimate strength of the FRP material. Moving on to the member's resistance, as you can notice, the equations are the same as steel angle section. The only difference is the resistances that are calculated for the hybrid members and are highlighted with the red line. The results of the test on hybrid members were compared with the results of previously executed tests on same angle members without any FRP strengthening. In the diagram, you can see the increase in ultimate strength of the hybrid members. As you notice, the increase is larger when bending is about weak axis for the bending specimens, and for the compression members, the increase is larger when the members are slender. In some cases, when we have centrically loaded specimens, the increase is really huge. You can see that we have an increase of 25 to 2.5, which is a significant increase. In this diagram, moving to this diagram, you can see a comparison of the experimental ultimate load and the ultimate load that was calculated based on the formulas that, the analytical formulas that were presented before. In the red line, you can see the points that we have equal experimental load and analytical load. As you can notice, it is obvious that we have a good match of this estimation, the analytical and the experimental, and the rest of the cases we are in the safe side. In some cases where we have pure compression, where we have loaded centrically, there is a big overstrength that was observed also in other specimens and in other tests in other universities. And in these cases, the ultimate load is similar, is equal, or even bigger to the critical backing load. But the design formulas are not calibrated for these cases, since we have a very good match with the other cases where we have either bedding, pure bedding, or compression and bending, strong axis and weak axis bending conditions. I want to close our presentation with an example of the application of these design rules to a typical telecommunication tower. In this type of tower, a common failure occurs in the middle part of the tower. It is the part above. It is the part in the head above the change of the leg inclination. In this part, a failure occurs in braces, so we have chosen to strengthen these braces only by adding FRP plates, as it's shown in the figure and the pictures next to this, to the slide. Based on the new design rules that were presented previously, we can have a significant increase in buckling and tension resistance. You can see that we have an increase in both resistances, but in tension is bigger. But also we have a significant increase in back resistance, because this failure is a buckling failure. In the conventional strengthening method, we can use another larger angle instead of these failed braces, or add another brace to build a built-up member. In the innovative solution, in the strengthening method with FRPs, we do not use any other steel section or members. We just apply FRP on the members, as you see in the figure. The big advantage, the major advantage of using FRPs is that in the conventional method, strengthening method, we have an increase in total weight of the tower and also in wind action, because the wind reference area also increases. In the innovative strengthening method using FRPs, we do not have any increase in the weight. We just use the same sections, angle members, and we don't have any increase in the wind actions, because we have the same surfaces, the same wind reference area. So, thank you very much.
Okay, thank you very much. So the next presenter will be Professor Dimitrios Vamvatsikos and Dimitrios Bilionis from the National Technical University of Athens about the risk assessment of lattice towers. I would invite them to speed a little bit up to stay within the indicated timeline. Thank you. You have to unmute. You have to unmute. Dimitrios.
Unmuted. Good morning, everyone. I'll be sharing this presentation with Dimitrios Bilionis, who's about to get his PhD on this. And we'll be discussing a little bit the idea of assessing the risk of lattice towers. In general, we'll be discussing a couple of different types of lattice towers. So we'll give you some idea about performance-based design basics, discuss a suspension transmission tower as just a case study example. This is the one that was designed earlier by Mike. And we'll show you the risk estimation for 2 locations in Germany. Just to give you a general idea, consider this part as, let's say, the fun part where you have done your work, you have created your constructions, your formulas, your expressions, you've done your design. And the question is, okay, so if I put it in a crash test, how will it perform? So this is the crash test. Of course, it's fairly expensive to do a crash test like you would do in the car industry. So you do it in simulation. Again, the types of towers we've worked on, you've seen part of them. This was the telecommunication tower shown earlier by Konstantinos, the suspension and the transmission towers shown earlier by Mike. And the general formulation is fairly simple. You're discussing risk as a convolution of fragility and hazard. Now, fragility, the risk actually, is something that incorporates the characteristics of the structure itself and, of course, of the site, the hazard of the location and site. The fragility part, which is this one, the first term in the integral, is essentially the probability of failure of the structure under a specific level of the intensity measure. And you also need to account for multiple scenarios, okay, of different probabilities of wind and types of wind and ice all together in different directions, acting on the structure itself. And the hazard is pretty much how often those hazard scenarios will occur. So put them all together, you get your risk. It's easier than it looks because in reality, you never really integrate. You just sum over a lot of scenarios. The environmental hazards in our case are going to be the extreme wind speed and ice accretion, and they're going to be estimated by meteorological data from weather stations. I believe there is a presentation later on that discusses this in more detail. And for the structural response, now we cannot use an elastic model. We had to use a parametric nonlinear model, which is capable of running dynamic analysis very quickly and run them en masse. So that's important for doing this. To give you an idea, the next to discuss this is going to be Dimitris. And Dimitris, come over, please.
Hello, thank you very much, Professor Vamvatsikos. I'm going to share my screen now. I hope that everyone can see my screen. And I'm going to present the case study of the risk assessment of the suspension transmission tower. Mike previously gave the specifications of the suspension transmission tower. It has the typical Danube tower and with a height of 50.20 meters, 2 cross arms. The lower cross arm carries 4 conductors, while the upper cross arm carries 2 conductors. There is an earth wire on the top, and it is constructed only by angle sections. And we assume that this is a part of a power line with spans equal to 350 meters. In order to perform the dynamic analysis, we should create a 3D FEM model. For this task, we used the OpenSea software, and we ended up with a model of 982 members. The members consisted of fiber sections. We designed the legs as beam elements and the rest of members as truss elements, and the earth wire was modeled as a spring element. And finally, we consider 5 ice thickness scenarios, 1 scenario for no ice conditions, and 4 scenarios for various ice layer thicknesses. These are the results of the model analysis, and I present the first 3 modes. As we can see, the first 2 modes are longitudinal, and the first mode is along the y-axis, while the second mode is along the x-axis, and the third mode is the torsional one. The aging periods for the first 2 modes are 0.51 seconds and 0.50 seconds respectively, while for the torsional mode, the corresponding aging period is 0.43 seconds. Then we investigated the expected failure mode, and we found, running pushover analysis, that the first failure occurs close to the base at the rhombus. And this failure mode seems to be consistent with failures that have been observed in previous events of tower collapses. And in this slide, we can see some pushover curves for the various ice thickness scenarios. I should say that the load factor is a value, and when it takes the value of 1, corresponds to lateral loads calculated with the basic wind speed at 10 meters, which was 25 meters per second according to the German annex of the Eurocodes. And for the no ice condition, we found that the first failure occurs for a load 2.18 times greater than the basic wind speed load. Furthermore, as ice thickness increases, the load factor and thus the corresponding wind speed of first failure decreases. In order to evaluate the effect of wind, we first need to simulate wind speed fields. Wind speed fields can be simulated by the TURBSIM software, which is provided by the National Renewable Energy Laboratory of the United States of America. It has the capability of simulating a 2D wind field. At this task, we decided our field to have a length of equal to 2 spans. This means 2 times 350, 700 meters. The software can output wind speed time series at different heights in 3 directions, X, Y, and Z. Based on the values of the wind speed time series, we can estimate the corresponding wind forces on the tower body and the conductors. As far as the effect of ice is considered, we should say that ice affects both the dead loads of the tower and the conductors, and in specific, it increases the dead loads, and also ice increases the areas of projection, and this results in increasing the wind forces. In order to simplify our calculation, we assume that a layer of uniform thickness is accredited on the surface of the tower members and the conductors. And for that layer, 4 scenarios of thicknesses of values 1, 5, 10, and 15 millimeters were considered. The first step in a risk assessment is to estimate the fragility of the structure. The fragility of the structure is a characteristic of the structure. And in order to estimate the fragility, we should follow the following procedure. First of all, we should simulate a large number of time series of wind speed for specific mean values, like in an interval, let's say from 15 to 35 meters per second, with a specific step. And this process is done in TURBSIM. Then, based on the results of the time series of wind speed, we can estimate the corresponding wind forces on the tower and the conductors for various ice thicknesses and various wind angles of attack. The next step is to perform the dynamic analysis in the OpenSim software, and in that step we use as input the wind force time series that we estimated in step 2. While performing the dynamic analysis, at each of the dynamic analysis, we can estimate the engineering demand parameter of failure. In our case, we decided the parameter to be the maximum top displacement in the transverse direction. Based on the OpenSys results, we can estimate the number of failures for each wind speed and thus the corresponding probability of failure. And the final step is to estimate the fragility curve. In these graphs, I have depicted some fragility curves for some icing scenarios that we estimated. First of all, we should say that a fragility curve provides the probability of failure against wind speed. And we usually assume that it follows a log normal distribution. And one can construct one fragility curve per each combination of wind speed, angle of attack, and ice thickness. An important value in a fragility curve is the median wind speed. The median wind speed is the value of wind speed where we expect a 50% probability of failure. For example, for the no ice conditions, the median wind speed is close to 30 meters per second. While if we go to an adverse scenario of icing conditions, that with of thickness of 15 millimeters, the corresponding wind speed is much lower and close to 20 meters per second. So we can infer that as ice thickness increases, the median wind speed of failure decreases. finding which is reasonable if we take into account the effect of ice on the increase of the wind forces. Let's now talk about the hazard estimation. The hazard estimation is the second element, the second quantity that we need for the risk estimation. In our case, a hazard is the probability of occurrence of combinations of wind and ice conditions. In order to estimate the hazard, we need some meteorological data that are provided by weather stations, such as the wind speed, the temperature, and the precipitation rate. For the wind speed distribution, the calculation is pretty much easy because we can just get the measured wind speed values in the weather station and do some distribution fitting and extract the wind speed distribution. While for the ice thickness distribution, our task is a little bit more difficult because there are not ice is not measured at weather stations, so we have to do some calculations based on empirical models such that of zones. As I have already said, hazard depends on the site of installation. It is site specific. So for our case, we decided to use meteorological data for two Pontesian tower sites. Both are close to the German borders with the Czech Republic. The first location was from Meirenberg and the second one from Fichtelberg. For both sites, the period of data available was from September 1995 through the last day of 2018. So we had a long period of data available. And also we should mention that both sites have the same basic wind speed, 25 meters per second, according to the General National Annex of the Eurocode. In these graphs, we can see the joint wind speed and ice thickness distributions. In the left graph, we can see the distribution for the site of Meirenberg. As we see, the wind speed, the expected wind speeds are lower than 5 meters per second. And also the ice thickness is lower than 1 millimeter. While for the case of Fichtelberg, we expect higher wind speeds. As we can see, the probabilities of wind speeds up to 10 or even larger than 10 meters per second are non-negligible, while the ice thickness, for the ice thickness, we have similar results with the site of Meirenberg. However, in terms of wind conditions, we can say that more adverse conditions are expected in the site of Fichtelberg, and we will see that impact in the results of the risk estimation. So, in order to estimate the risk, we have, as I said, on one hand, the probability of failure, which is the structure specific, and it is provided by the fragility function. And on the other hand, we have the probability of occurrence of wind speed and ice thickness combinations, which is site specific, and it is the hazard. So, to estimate the risk, which is the probability of failure of our structure during its service life, we simply need to combine the fragility and the hazard, and this can be done by estimating this integral. In this integral, we can get the value of lambda, which is the annualized probability of failure, by combining the probability of failure for a given combination of wind speed and ice thickness, provided, and this is the value of P, a demand exceeding capacity for a given wind speed and ice thickness, and it is provided by fragility, and also the probability of occurrence of the combination of wind speed and ice thickness, which is provided by the hazard. So the results of risk estimation for the two sites considered in our study, we can see that for the site of Marienberg, the annualized probability of failure is equal to 0.0030, which a value that corresponds to a return period of 333.25 years. While for the case of Fichtelberg, the annualized probability of failure is much higher, and it is equal to 0.0481, and this corresponds to a much lower period, return period, which is close to 20 years. So we should note that we assume that the same tower was used in both locations, but the stronger weights are expected at the case of Fichtelberg. So we should say that probably that that model of tower is not suitable for the case of Fichtelberg. And this slide concludes our presentation. Thank you very much.
Thank you very much, Dimitrios. A very nice presentation. Now I would invite Mr. Friehe from the University of Aachen to make a presentation of his nice tool that he developed in the framework of a FOSTA project for the optimization and the design of steel lattice towers. So this is also now the end of the presentation for the RFCS project ANGELHY, and we will now conclude with two presentations from the University of Aachen with really nice results. Hopefully you will enjoy. So Mr. Friehe, I will give you now the screen.
Yeah, thank you. Thank you very much, Mr. Tibolt. Can you hear me?
Yes, very well. We can see your screen and we can hear you.
Oh, perfect. Yeah, thanks for the friendly introduction. So my name is Mirko Friehe. I am research assistant at the University of Aachen. And oh, can I switch? Next slide. Okay. And in the past, we had two research projects, or rather one of these projects is currently still being worked on. One project was we called OptiWind, and the other is Hightower, together with the IGF. Both projects are IGF projects together with FOSTA. And today I want to show you a couple of main results coming from the projects. And this is the design tool for dimensioning and optimization of lattice towers. So with the publication of the Hightowers reports, the software tool we designed here will be published as well. So it's just for your information. So one target of the project was to find an optimal truss structure. Yeah. So what does it mean, optical truss structure, or what is the procedure to design an optimal lattice tower? So in the first step, you need to define the structure, yeah? The topology, the cross-section, what kind of cross-section type do you choose, the dimension, and so on. So the topology. The next step when you design a tower is to determine loads, wind loads, for example. I've shown here in this case. So wind load is the main load for those structures. And in the next step, once you have defined the wind load, you need to do your design and choose a cost-effective construction method. Yeah? And of course, if you change the topology or the geometry, the wind load will change as well. So to get an optimal truss structure, you need to optimize it by hand because it's an iterative process. Yeah, it's really hard to make it by hand. So this is the reason why we have decided to create a software tool from these projects now. And this is the tool I want to show you today. So So again, in the following slides, I would like to discuss these 3 points, yeah, and how the tool will handle them. So the first point is definition of the structure. So of course, there are different types of truss structure. For example, a K, an X, or a Z, depending on the load situation. For example, an X, of course, is much stronger than a Z truss. And we have decided to create, let me say, objects in the software where each object is one truss type. Yeah? For example, a K, an X, and an XH. And to increase the bearing capacity, sometimes you add, or you can add, additional members to the truss section to reduce the buckling length. Yeah? For example, if you want to get stronger K truss types, you can just add, let me say, secondary elements, which here decrease the buckling length. So. And if I want to show this in a matrix, yeah, you can see here a K value, X, and Z value. And by adding elements, we get a huge matrix of objects. And all these objects can be created in the software. And I think with those objects, it's almost, you can build almost every truss tower. So if I want to build, let me say, almost every truss tower, I can parameterize one object. For example, I can define the height, or the width at the bottom, or the width at the top, and of course, profile types, profile dimensions, different sections, connection steel grades, and so on. And for example, for given load, the software can vary these parameters to find the most cost-effective variant. So what the software is doing, let me say, for a given load situation, for example, a given load situation, a given wind load at a special construction site, the software will iteratively, like a try and error, try all possible, try to get all possible combinations, and will, let me say, now I need to, here's the video. Yeah, this is what the software is doing. Yeah, he has a, let me say, a list of possible truss types, and he will try every object in the list, and the one which has the lowest weight, so it's everything is about the weight, this one will win the race. That's just a video how the software is doing it. And we can do it for every height, and so we can create a huge truss tower. Yeah? Sorry. So the second part, how to optimize lattice tower, is a realistic wind load assumption. I will get very quick through it, because the next presentation, Mr. Kemper or Professor Kemper will show you much more in detail how to get realistic wind loads. I need to close that here. Sorry. So one part is to use direction-dependent wind speed. Unfortunately, the Eurocode does not provide direction-dependent wind speed or direction-dependent gust velocity pressure, and therefore you need to go to a weather station. It's not so complicated, but it is one part how to optimize lattice towers. In Germany, usually we have the main wind loads coming from west-southwest. The second part is using direction-dependent force coefficient. Coming from wind tunnel test or from the Eurocode 331. So the project, the two research projects, we have performed a couple of wind tunnel tests with the L profiles, with the double L profiles, and of course, what we have done also are towers with 6 legs. Yeah, wind tunnel tests with towers with 6 legs. So the dimensioning, a huge topic in the software. I will go through it very quick. The dimensioning is only based on the Eurocode, Eurocode 3.3. Here's an example of a tower. Of course, it is the tower consists of different parts here. For example, of leg members, of primary bracing, like the X members in an X truss, and secondary bracing. And I mean, that's clear. Those structures have a very high risk of stability. So the stability design is the design that matters. You know? So we wrote a software tool where we did the dimensions according to Eurocode 3.1 and 3.3.1, but I'm focused now on 3.3.1. Maybe I will show you some small difference between those Eurocodes. One difference is the cross-section classification of angle members. In the Eurocode 3.1, it's here for class 3 h/2, and in Eurocode 3.3.1, it's h minus 2 times t over t. In the software tool, we have we use those cross-section classification for L profiles because it's all about towers. And the verification according to Eurocode 3.1 for buckling, I think this is very straightforward. This is a bearing capacity for the buckling resistance. You need to define slenderness and so on, and it's more or less it's you need to define for Euler cases, yeah? And this matters for one single members. And if you want to use, for example, 3.3.1, they try to give you some equations where you can handle those structures, so truss structures. Yeah. So it's more or less the same. They define different slenderness, different reduction factors. I don't want to go very much in detail. I just want to show you it has a lot of situations, different situations. I'll just go through it. So effective slenderness reduction factors, depending on whether it's a leg member or it's a primary member or secondary member or whatever. You need to define slenderness factors, depending on truss type, whether it's a symmetrical bracing or an unsymmetrical bracing. Again, here reduction factors, depending on the ratio normal force, tension to compression, and depending on the connection type here. So there are many situations you need to take into account, and all those situations are implemented in the software. And I think the best thing is that I can show you the software or give you a small view into the software. Hopefully I can do it here like this. Can you see it?
Yes, okay.
Okay. So this is the software tool we will publish with the Hightower project, and it can do more or less the things I've given you in the slides. Let me start with generate truss tower, and I can click here on. Unfortunately, it's in German, so I try to translate it. You can click here on generator structure. Now, you cannot see a second window, right?
It is now opening.
Okay.
Generator. Yes.
Okay. Perfect. So, for example, we want to create a tower with 4 legs. Let me say we begin with a K truss. Then I just click here on K truss. Then I can modify the properties, width at the bottom, width at the top, height, and so on. I can choose the profiles here, whether it's a leg member or it's a diagonal, whatever. Let me choose here a huge L profile, for example. And when I click on create structure, the software will create here automatically a K truss. I've chosen a huge leg member, so you can see the leg members here. And for example, if I want to create a whole truss manually, I can add here some more X trusses. Here in the window, you can see I have at the bottom a K truss, and then I have 1, 2, 3, 4, 5, 6 X trusses. And if I create if I click on create structure, you can see I've built a not really realistic tower, but anyway, it's the topology is here in the FE model, and I can, for example, let me do some very weird thing. For example, in the middle somewhere, I change the width, and you should see here a very weird tower, yeah. And the next step is the software can create wind loads automatically. Yeah? So when I click now on generator loads, I can create wind load. It's a wind load generator. Yeah? So I can define here, for example, the gust velocity pressure, and for different angle of attacks, I can define different factors. Yeah, so I can create different wind pressures from different angle of attacks. And now I've created, for example, the wind load, and here you can see here the wind load is automatically created to the FE structure or to the FE model. Here, and then I can calculate it somehow. Now it's I need to do it like this. Can calculate it. And you can see here, let me say the amplification like this. Now we have a huge deformation of the tower. And the dimensioning or the verification is also done. So now I need to check it here. Here are the verification according to your code 3. And for example, if I go to bending, buckling, of course, we have verification of bending and so on here as well, but buckling is the most that matters. For example, of a combination here, then you have for each member, you have the design here. Now it's not optimized because I did it by hand, no? So this one will not work, but it can do the dimensioning automatically. So this is the way how to use the software by hand. Of course, I've told that I have a tower generator as well. So you can here, for example, the tower generator, you can define a tower height starting with at the top, a maximum inclination, different possible inclination at different heights. You can add, for example, for leg members, let me say I want to have a tower only consisting of L profiles. Yeah. So now I have a list of L profiles. And now when I click on generate, the software will try to get the best or the optimized lattice tower according to the, let me say, yeah, according to the values I've given here. Yeah. Yeah, I think that are the main parts. We have some other, we have a probabilistic calculator here, but I think I don't have the time to show it. But maybe if you're interested, I think maybe in the mid of next year, the software will be published with the project. Okay, thank you very much.
Thank you very much, Mr. Friehe. Very interesting. And now we come then to the last presenter. This is Professor Kemper, which will give an overview on, I will share my screen so that you can see. The last presentation is about the wind loads on steel lattice towers from Professor Kemper, also from the University of Aachen. So I give now the screen.
Thank you very much, Mr. Tibolt. Thank you, everybody, for inviting me for this presentation. And I'm sorry I came a bit late, so I missed, unfortunately, some of the first presentations because I was in an CCS meeting before. But I stepped into the presentation of Dimitrios Bilionis, I hope I pronounced it right, which was very interesting to me, and I hope I can have the opportunity to see it later on in a full version. So our topic is quite connected to what he has presented, and it's of course quite connected to what my colleague has presented just before, because we are in the same working group. It's the Center of Wind Engineering and Earthquake Engineering of the Technical University of Aachen. And our main focus is wind engineering, and that means wind loading on structures and what structures are doing if they are affected by wind loads. So I want to give you an overview about this topic today, and to go sometimes, and I want to go sometimes a bit into details to let you know what we have found out with the ongoing research projects. A part of that you have already seen before. So I would like to start with the influence parameters of wind loading. And of course, we have to take into account the location. Where do we want to erect a structure? Then we have to take into account the geometry. And finally, and maybe that's not really clear for everybody, we always need to take into account how does the structure respond on the wind load. And I will come to that a bit later then. So first of all, the location. I think you heard before in the presentation that I have just mentioned that, of course, we've got different values of wind speeds. And in that presentation, I heard about icing. That's, of course, a topic as well, also for us. And normally in a design procedure, you would not go into these meteorological data. You would just pick out a value out of standards. For example, here, the example of Germany, which is divided in 4 different wind zones. And these wind zones gives you a basic velocity of the wind, which means it's a 10-minute average value of wind speed for rural terrain in 10 meters heights, return period 50 years. So
Professor Kemper, I think we lost your voice.
Weather stations here distributed all over Germany. But of course, such weather stations, they exist all over Europe as well in a similar density. But at the time being, we only have access to the German data. So what we are going to do, you could see in the presentation before, we like to do automation, and we are currently automating the analysis of the weather data as well. That means we take into account for a given location, nearly located meteorological stations, and then we make an analysis automatically in order to derive basic velocities. So this goes beyond what is provided in the standard with the simplified wind zone map, and you can imagine it's more realistic doing so. And another advantage is with that, it's possible to have directional values as well. So it's not only that we have the values from all over, from all directions, but we have them for different kinds of sectors. The second is then the basic velocity is not the value what we really need for the design at the end. We need gust velocity, mostly gust velocity pressure. And in order to derive that, we need to know that we need to take into account wind speeds with a shorter averaging time. In this case, it's 3 seconds. So it's the instantaneous gust speed, which is affecting the structure, which is decisive for the design. To do so, we need to take into account the turbulences, and turbulences, they arise due to the topography, how the surface is used and how it looks like. Based on standards, there are some recommendations how the topography should look like in order to give or to associate a specific value of roughness. But what you need to do then is you need, like here, a satellite photograph, and then you need to check what kind of terrain do we have there, and then you just do it by your eyes and to select then a specific value of roughness. So that's not very precise, and of course this quite needs some time. And this is what we are currently doing. Again, it's an approach based on automation. This is a quite new project that we are starting now. Here we are using a database, a GIS database, which is called Corinne. This exists for all Europe, and it has values for the information, how is the landscape used, and based on that it is possible then to associate roughness. And what you can see here, if I try to, no, I can't stop the presentation there, but what you can see close to the lake where the roughness is smooth, you can see there is a unique color, in this case it's red, and that means the roughness from this wind direction is smooth. So we are able to automatically find precise values of roughness based on this database. So what we are aiming for is then direction-related wind speeds, because we know it is much more realistic to take into account all the different angles of attack, and this needs such an analysis. So this is plotted here just to give you an impression what can turn out. For example, in the middle, you can see velocity rows, which gives you the probability of occurrence of different wind speeds from the different directions. So at the end, this highly stochastic, time-dependent process, wind, is then simplified to a profile, height-dependent profile of velocity pressure. But it is a quite realistic simplification that we can make if we take into account the directional values. The next topic is then the geometry. This is just an example of geometry, and if I start this animation, I hope you can see that, what happens. So this is related to aerodynamics. The flow which is going around the structure, of course, it leads to different pressure distributions, and because of that, we've got different forces acting on structures, and that's what we need to take into account in the second step. And with respect to lattice structures, we've made a lot of investigations for that, because due to the complexity of these structures, due to the number of elements, it's not that easy to find just one value to describe the aerodynamics. You need to investigate quite a lot for that. And first of all, I like to share here the given recommendations based on standards. So this is Eurocode 1, for example, for 3 or 4-legged lattice towers. And you can see at the lower part that we have different degrees of opening here. And for those different degrees of opening, there is a value which describes the aerodynamic behavior, which is the force coefficient. So these values are non-directional. So the advantage that I showed you before, where we could have directional values for the velocity, you will lose it if you do not have aerodynamic force coefficients, which are also taking benefit of directional. So that means it is safe because it's a worst case value, but it's not realistic. Then there is a newer approach given in Eurocode 3, part 3.1 for towers. I will speed up a bit just to let you know that here it is possible now to take into account the direction as well. And here a distinction is made between sharp-edged profile cross-sections and circular cross-sections. So there is an influence of Reynolds number due to aerodynamics. And with this approach, this can be taken into account. So if you have a lattice which is mixed with sharp-edged and rounded cross-sections, this can be considered here. So what you do then is you find the ratio of the cross-sectional area and the projection, and then you can derive a value which describes the aerodynamic behavior. So at the end, as I said, directional coefficients for different kinds of 3 or 4 legged lattice towers. This is possible based on that. But we had a problem during our project OptiWind, which we faced because in that project we have investigated lattice towers for wind turbines, and those kinds of lattice towers, they have a very low degree of opening, and for those kinds of lattices no aerodynamic coefficients have been investigated yet. So that's why we did that using our boundary layer wind tunnel in Aachen, and here you can see some model pictures, and there is, as an example, the K-truss, which Mr. Friehe already showed before for his optimization strategy. And here you can see how we have investigated aerodynamic coefficients for exactly this structure. So we made a fitting for direction-dependent analysis so that in the optimization strategy, this could be used. So this is an example what turns out based on such a wind tunnel measurement. Those are force coefficients over 180 degrees plotted here. You can see there is not a very high variety, but there is some. And the values are roughly between 2 and 4. This is just for one model, what we can see here. Of course, we can expect symmetry. I just showed it like this because the numbers were quite small. So here the numbers are also quite small, sorry for that. Just to give you an overview how many different kind of cross sections have been analyzed in wind tunnel tests. So we do know much more now. We have confirmed values for the directional dependent aerodynamics. This plotted afterwards to give an idea what turns out as, let's say, overall values in a comparison to what has been plotted in the standard. And what we can see here, the values of the standard are safe. That's not always necessarily the case, but in this case it's true. And this also means we can save some wind loads if we go more into detail. And this is just the overall value. If we do make a design which takes benefit of direction dependency, then we can save much more. Yeah, some words to ice loading. That's why I was really interested in the presentation I mentioned already before. So we are also focusing on ice loading and what does it mean in combination to wind loads? Because of course, if you have a cross section where you have ice, this is one effect. And the other effect is if there is a situation where we have ice on the structure, then we can assume we will not have the extreme 50 years wind storm event at that time, at the same point in time. So that's a question of correlation, load correlation. So what we are doing here is we are investigating the criteria for ice aggregation, and then we sum up how many ice is covering the cross sections. And with the tool that I presented at the beginning, the automatic analysis of weather data, we can then also analyze for those days where we have icing criteria, what are the associated wind speeds, and then we can make an extreme value statistic afterwards in order to find basic velocity, which are much lower because they only occur during the points of time where we have icing conditions. So we will have reduced wind speeds and a value for ice attachment based on these analyses. So this is an example. We're working on experts' reports, for example, for different tower structures in Germany, where it's interesting to know how many ice do we need to consider for the design. And this is based on such an approach then. Yeah, finally, just some comments to the next point, which is taking into account the structural response. And taking into account the structural response, that mainly means for tower structures to take into account the gust response, because due to the turbulence of the wind, we have resonance response of the structure. And normally, this is taken, oh, I'm sorry, it's still German. I thought I have modified that. So it's described by two aspects. The first one is the background aspect. That means, or this is due to correlation of gusts. And the second is resonance. This is due to the dynamic behavior of the structure itself. And if this is taken into account, then the inner stresses in the structure, of course, they are different than just assuming it's static. And that's why we need to take it into account for the loading, because at the end, a safe design is necessary. And this dynamic amplification is present due to the gusty wind. And that's why it's part of wind engineering. So in this slide, I can give you a very quick overview about the effects which are taken into account. On the one hand, it's the gust energy content, then the correlation, which is described by aerodynamic admittance, then the structure itself, depends on frequency and damping mainly, and finally what is happening at the structure. And this structural response can be distinguished, now it's coming in English, in the background part and the resonance part. So this is a spectral description of what is happening inside the structure. And in the upper right of this slide, you can see the formula for the structural factor CSCD. This is part of Eurocode 1, and I know for those who are not working daily with this kind of values, it's a bit confusing because it's not really well explained what influences what. And we made a recommendation for a first check, which has been published in the Stahlbau calendar in Germany. And this first check, for this first checkup, you just need to know frequency and damping, and then an eta value, which is based on wind zone and roughness category. And then you can have a first estimate to what extent you can expect a resonant response. All right, so my last slides, just to give you an impression, the world is not only a 1 degree of freedom dynamic system. We also are working on wind energy turbines, for example, in the scope of the Foster project OptiWind. And there you can see this is again a spectral description for the structural response, like I have shown before. But in this case, of course, we've got a lot of more degrees of freedom, and that's why the spectra differ. And in this case, we've got a comparison based on a frequency-based approach and based on a time-dependent approach. So at the end, just one comment to reliability. And everything what I have shown before means we are more and more able to consider reliability in such a way, because we know much more about the realistic loading, we know much more about the realistic effects, and this is very necessary in order to perform such a reliability analysis, because you need to know about the variety of the influencing aspects. Yeah, and that's why we are very thankful that we could have worked on these interesting projects. And with this, I'd just like to thank you for your attention. Thank you very much.
Thank you very much, Professor Kemper. Very interesting topic that you are presenting. Also for Mr. Friehe, this is very interesting to see. And I think it shows that even if we think that we construct already lattice towers still years and years, nearly 100 years and even more, concerning the design, there are still open questions, and there's still a need for further research to optimize the structure, especially now with the tendency to go toward more green energy, and where we need, yes, windmills. Yes, which can be tubes, but also lattice towers, and also for the energy transportation, new grids that we have to construct. And I think it will not be only limited to Europe. Of course, now for the project ANGELHY, because it is a European funded project, we focused more or less on the topic of Europe, so on the Eurocodes, not especially now on the American standards, but I had this question. It would also be nice to compare it. we have the tendency to also compare it to American standards, but of course not in the framework of ANGELHY, because this would have extended the scope, and also based on the European project, we say we will limit on the European codifications. I think now we came then to the end of the presentation. I saw that Dr. Nüsser from Foster joined, and I would take the opportunity to thank also Foster for their significant support in the organization of this webinar. And especially so, Dr. Nüsser, thank you very much for your support. And I think it was a nice webinar where we show all the ongoing research and also the needs for this research. Now, if there are still some questions, you can write it down in the Q&A stick, and we would be ready to answer it. I think in the meantime, all the questions that we got were answered. But of course, if there are still some other questions, I think we still have time, 20 minutes, perhaps it's a little bit much, but you are open to ask. Here I got, for example, a question if the handouts will be made available. I think yes. Concerning ANGELHY, we do not see any problem to prepare and to make them available online. What we can do is, because we have your email address of all the attendances, we can also make it together in a PDF and send it to all the participants. I think this is not a problem. For the University of Aachen, I don't know if we can share, or if you are willing to share also your slides with the attendancy. It's up to you to decide if this is okay or not.
Yeah, from our side, it's very okay, yes.
Okay, perfect. So if you could then send me your presentations, I will then share them with all the participants of this webinar. So I think we can wait a little bit. If
Mike, we can certainly make a PDF of our presentation and send it to you.
Yes.
And then you can handle it as you think appropriate. Yes.
Yes, the best way is that you send everything to me, and then I will share it with the participants. This is possible without any problem. So we got here one question. Yes, here we have one question. Thank you. Would it be sufficient to demonstrate the reliability of your own basic wind speed prediction if we report all our steps, extreme value analysis in the calculation? If there's somebody who would like to answer for wind speed prediction.
Yeah, maybe I can answer on that. So if I got the question right, it's related to whether it's allowed to take into account meteorological data in order to make a direction-dependent analysis. And the answer is, from my perspective, totally yes, because there is a so-called opening clause in the Eurocode that in case that appropriate statistical methods are used, then it's allowed to make use of such kind of methods. But as you said, of course, it's necessary then to make it open. And according to our experience, maybe there is less discussion if such a report is coming from an institute. I'm not sure, at least I haven't faced reports where it is just a part of a structural calculation, let's say, from an engineering office. But generally, it should be possible as well. Maybe it's a bit more discussion at the beginning. I'm not sure about that. But principally, this should be possible, yes.
Okay.
If we do not have questions, I would like to have a question to Professor Kemper. Because of the slide, the last slide that he showed us, it was about the partial safety factor design. It came to my ears that in the future, we will not work, this methodology has not a big future, that in the future it is towards risk assessment of structure. What does he so directly evaluate the risk? What is his opinion about that? And so
thank you for
accordingly, a very important thing is to include such methodologies in our syllabus in the university.
Thank you for that question. I think there is a good reason why we have this partial factor approach, because if you really want to go into risk analysis, you need to know a lot. And normally you cannot know all the details because you need to know the variety of the influencing effects loading. You need to know much more about the load correlation, and you need to know a lot about the resistance and the variety of the resistance parameters, which is not only yield stress, which is much more than that. And that would mean it would give you a feeling of safety where you do not have that safety from my perspective. And the simplification which has been made with this partial factor approach, I think it was a quite intelligent choice, because of course there's still the same problem, but it has been answered once with these parameters alpha E and alpha R for the effects and for the resistance part. And so there is no discussion about that. But if you open that up, then it would mean you need, like the question before, is it allowed to make use of metrological data, for example? You need to make clear what kind of data has been used for the risk analysis. So I think that would be the problem then. So is the data that has been used valid, and how has the analysis been made? So I would see much more problems about that. But of course, in the field of universities for research, I think we should focus on that, and we should clarify in what extent maybe we can improve the partial safety factor approach for practice. I think this is still the right procedure for practice. But of course, there is always a tendency to get more realistic on the other hand, because that's also a question of sustainability and economy. And that's why I think both paths need to be followed. But for practice, from my perspective, it's far too early to see risk analysis for the design. Do you have another opinion about that?
Okay, you refer to, let's say, to the broad civil engineering application, but we have a lot of structures that are handled as products. For example, as wind turbines. So this is more or less a product that is sold. So probably there, which is placed, let's say, this product in one place or another. So probably it would, I don't see in which future, but it would start such an application of in such types of structure, and then extend up to cover, let's say, more buildings or more types of constructions.
Yes, I agree on that. If there are restricted boundary conditions, let's say, and you can ensure manufacturing process and get the parameters which are needed, then I think this is much more realistic. And another field may be if you want to make use of an analysis of existing structures for the future usage, for example, and you make an investigation about what actual parameters do we have by investigations. This could also be a field, and I think in both cases it's quite realistic that risk analysis is used. Yes, I would agree.
Okay, then we have another question. If we would have info about Eiffelized angles for lattice masts with triangular plan, any document, any supplier, Here I can tell that I have some documents on it that I can share. That's not a problem. But if you could just detail what you mean by eyeflies, is it really just that you have the tubes with the bracings in between, or are you also talking about real angle profiles? Real angle profiles, yes. Okay, that's not a problem. I can share a document with you. I put down your name. I normally have your email address. So I will send you this document on it. That's not a problem.
Probably should, yeah.
Yeah, for that it's fine. But I think also another question that was done during the presentation was about the surface condition to apply the CFRP strips, especially about sandblasting. And of course, if we sandblast or if we need to sandblast the profiles to apply the CFRP strips, of course, it would be a disadvantage if you would have to do it in big heights on construction site, because we can easily imagine that this is very difficult. So I think we should also look if it is possible to have a surface condition in which we can apply these CFRP strips, which can also be easily reproduced on construction site. And I think we are aware of this problem, and we are also trying to find a solution for it. Of course, the surface condition to apply the CFRP strips is one thing, but also you need to carry out or to take care about the corrosion protection later on. So meaning there we have to find a compromise that you can locally take it away, apply the strip, but at the same time, you should have long-term investigation to see also that the corrosion protection, even if you apply the strip, is still given. I think this is also something that we need to investigate. Of course, we cannot investigate it in the framework of Project ANGELHY, because this would just explode the frame. But I think in ongoing or former projects, this is one idea that we should keep in mind. Also to offer a practical solution on construction site to apply these strips.
We had anticipated a relevant proposal that
yes.
let's say to apply all this methodology in practice,
yes.
which will be done in the future. It's an important point to investigate.
If I may interject also a comment regarding the previous question about the risk and reliability procedure. Actually, by the way, thank you for this excellent slide. It really highlights a lot of important things. I would like to focus on the part that's called safety margin and appears on the screens. And specifically regarding products, structures as products, recent, let's say something that you can easily see happening in industrialized sections of, is that this safety margin by, let's say, designed by testing, highly optimizing the structure, which is of course something you want, right, is shrinking a lot. And if you look on the right side, when you're having like a lattice structure, which is pretty much a fairly fragile isostatic thing, you know, one member fails, the whole thing can fail. So this 5% fractal is something that can easily happen on the resistance part. If you go on the other side, where you have this 98% fractal, which is, I believe, coming from the 1 in 50 wind speed, automatically you get this weird discussion of, so you are okay with a lattice tower failing every 50 years? No, and historically they don't. And of course, then again, that yellow region, which has been very nicely highlighted, again, thank you for that, is actually something that we implicitly account for, we implicitly rely on. We want this to be there, but it's not really in the code. We just assume that it's there. So as you try to shrink it and shrink it and shrink it, it gets problematic. So in many ways, let's say I love partial factor design approaches, But in some ways, they can also be fundamentally flawed when somebody tries to exploit them and take them, let's say, out of context. And it's an interesting discussion where things like this tend to highlight it, show us, let's say, what you can err in the way of too much, let's say, optimization. But that's a long discussion.
Thank you very much for that comment. Maybe I may reply just shortly with one other comment, which sometimes our clients are giving to us, because they assume that what we can see here is as gamma E and gamma R, that this is the safety margin. Yeah, and that gives them the feeling of safety, even though they have effects which are not covered anymore. And I think that's what is very important to distinguish.
Yes, thank you very much for this comment, because I think this is very important to highlight that the safety margin is not just the sum of both, and that is a very good comment. So, okay, I see that we still have 5 minutes. I want to close really at 1 o'clock to respect the line, also not to occupy the line or the Zoom platform more than has been agreed. So if we don't get more questions, I would say we can nearly close the webinar. Again, I would like to thank then all the participants. Yes, also again the FOSTA, then the 2 presenters from the University of Aachen, Professor Kemper and Mirko Friehe, for their nice contribution to the success of this webinar. And last but not least, there is also what I would like to thank you is the Stelligent's communication department from ArcelorMittal, which offers us this platform and which organize in the background or what we were using. So thank you very much also for this.
Yes, and we would like to thank you for chairing this session and for all your perfect organization, Mike.
Yes, thank you. It was a pleasure, and I think the results, we have them. Now the next step is, of course, to put them together in a report and to publish it and to make all the results available. But I'm quite confident that in our nice group, we will manage this without major issues. So once again, thank you everyone for participation. Also the presenters, thank you very much. It was really nice to have this discussion and the presentation. Thank you very much. So I wish you a nice afternoon and see you soon.
Thank you, Mike.
Bye from Athens.
Bye-bye.
Yes. Bye-bye.
Bye.
Thank you.
Bye.
Bye-bye.
Bye-bye.
Bye-bye.